for the rock star of this blog, I want to introduce to Frank. Frank is a maker. He develops products and leads software engineering teams with a background in behavior design, engineering leadership, system reliability engineering, and resiliency research. At Slack, Frank focuses on making engineers' lives simpler, more pleasant, and more productive in the developer productivity group. So please help me with a warm welcome to Frank Chen.
All right, let's do it.
Welcome, Frank.
Yeah, let's do it. Hey, what's up, Draft? It's my first time here. It's so great to meet y'all. So hi, I'm Frank, pronouns he, him, and I'm excited to talk to you today about how Slack developer productivity teams introduce and think about circuit breakers. You'll hear about our motivation after a series of cascading failures that affected CI/CD, how we got there, and then how we changed our infrastructure workflows. Notably, many circuit breaker implementations are at the client or executor levels. We found benefits by implementing it at a higher level orchestration system. For many of you, this might be GitHub or GitLab. Finally, I'll be referencing good work that helped us understand this problem. You'll find linked to references at the bottom of each slide. In the coming month, you'll see a Slack engineering blog article with more details and code snippets from this talk. As we begin, this former academic's caveat: your infrastructure and problems won't look exactly the same as those you see today. But I hope we'll have some fun, and we can dive into any questions or things that are interesting to y'all. So first, we developed tooling that performed automated metric lookup for metrics across different Slack Prometheus clusters. When a metric reached a threshold, the circuit breaker would open up. When a circuit was open, our tooling would notify users in Slack and through our web front end that CI workflows were deferred or shed. Upon a circuit opening, a CI orchestration request would defer or shed the request, improving our queue management by keeping failing systems from executing requests. You'll hear about how circuit breakers broke the cycle of cascading failures, and we haven't had a cascading failure incident in the last 2 years. And finally, we'll talk about leverage. The same pattern I'll share is used in a variety of ways now internally. If there's time and interest, I have some appendix slides. We could talk through more in detail about our metrics-based anomaly detection, or how we integrate observability into these workflows, or how we're thinking of building automated deployment and rollback systems for every commit at Slack as it's released to customers. First, how many in this room have been a part of a cascading failure incident? Yeah, I think that's most of us, yep. Second, do any of your incidents feel like they're similar to previous incidents? Yep, pretty much same number, yep. So we had a series of similar incidents for months in 2019, starting shortly after I joined. I'll talk through some of the specifics, but again, they probably won't be the same as what you'll see at your org. The response and symptoms of incidents were similar, but were actually very different conditions. And I'm just going to repeat this one more time. Repeat incidents at scale, even at the same organization, don't happen. I found Laura McGuire recently wrote an article and shared a great way to frame this. Just as you never step into the same river twice because it is continuously flowing, so too will you never face the same incident twice, because continuous integration and continuous deployment means continuous change. So this is an example of a very bad week. We saw SQL contention that led to the first incident. The fix was executed by changing and patching the underlying system. In the second incident, we saw GitHub API load issues from latent requests from the previous day. Checkpoint is Slack's CI/CD orchestration system. Simultaneously, in the third incident, we tackled a series of Git LFS load issues, Checkpoint, and Jenkins queue management and scaling challenges for downstream services. It took 5 days to fully resolve. And again, these are all internal-facing incidents, so these hampered developers doing CI/CD. And a side note, like one positive outcome of this final incident was the introduction of using observability and cross-service traces. We added distributed tracing throughout multiple CI services to better understand and measure parts of our system that were behaving anomalously and discover previously hidden problems. And I'm sure you all have your own measurements, but developer productivity can be measured in a variety of ways. Time to merge, time to run tests, DORA metric, et cetera. But I can tell you what isn't productive. When there aren't large-scale incidents in your build, or test, or deploy, or release systems. You might ask, well, what were some of these problems? We started to see scaling vertically and horizontally weren't sufficient for our CI stack. Fast growth across Slack added complexity. The tipping point was reached around May 2019. And let's look at what that looked like. So again, customer growth looked great in CI. Over the last few years, from about 2017 to 2019, we're growing about 10% test executions month over month. So we regularly see new peak loads across services in CI. This means people were writing more features and more automated tests, helping your Slack experience be simpler, more productive, and fun. And so I spent a few months early on in 2019 working with our team and other teams on improving their performance, resiliency, and cost. You'll see the error rate in the next slide. I also wrote about some of those changes in that blog article. At Slack scale, this is in the hundreds of millions of compute hours per year. But how did we notice things were going badly? And so in this graph, you'll see a similar data warehouse query. The green bar represents error rate. And that's probably hard to read. Sorry about that. Look at the sudden increase in errors starting around May 2019, when we reach a tipping point for GET requests. We see a growth in the green error bars, which represent at least one incident per month that felt similar and cascaded between services. When code bases reach a certain files threshold, or the GitHub appliance reaches another threshold, a lot of out-of-the-box tooling starts to fail. And again, Git is a cornerstone of Slack CI and developer tools. Git scale problems are well documented with larger organizations that build abstractions, like Google's Piper, or modifications on source control, like Facebook with Mercurial. For example, in 2019, Slack's internal tools team adopted Git LFS to deal with large files. And during this time, the Git appliance was scaled up vertically. But we discovered, obviously, it wasn't enough. Incidents find a way. There's no one way to prevent all future incidents. You might ask why or why not. Well, what we found was like we had a lot of similar feeling incidents, and the response was almost the same, but the root causes and fixes we put in were all different. Service owners or backend engineers would typically build features until accidentally discovering a new way to redline some parts of the internal tools, or service ecosystem without a cohesive approach. We relied on developer productivity teams being paged and working with other platform teams and incidents to solve each new root cause. And finally, infrastructure and tests change all the time. They're each composed of many reliable components. Like all this is probably very familiar. Your network layer, retries all the way down. Slack client, retries from your app client. The AWS or dependent services Slack relies on, you guessed it, retries. And this talk is about internal tools, so test clients, async job queues, like retries all the way down at the suite level, test case, individual action, jobs, et cetera. So what's the takeaway? When you're working with very large distributed systems, you look under the hood and look closely enough, you'll see retries all the way down. Computers are terrible, yep. And so this diagram is from an internal deck on Slack's Webapp Architecture and presents a super, super high-level view of 3 major services that your Slack client connects to. Each of these major services has other minor services that accompany it. There are a litany of cool services that I won't have a chance to talk about. Your Slack client connects to 3 different APIs in order to present what users see in real time and efficiently. The Webapp API, it's responsible for all client writes, so these are messages, reactions, user profile changes. It's responsible for many client reads, for example, initial loading of channels, threads, activity. The Flannel API, it's an edge cache with multiple regions worldwide. It returns frequently fetched team-wide data, user info, channel info, emoji info, et cetera. The RTS API, this real-time server API is multiple regions worldwide, provides a long-lived WebSocket. It sends event-driven updates to the client. And so in distributed systems, circuit breakers are used to provide a degree of fault tolerance by detecting failure and isolating components to prevent them from propagating failures to other components. In doing so, these help maintain system availability in the face of failure. Clients are the typical places to implement a circuit breaker. And I'll talk through what these look like in our orchestration system and the benefits for circuit breakers here. And so I alluded to this earlier. Checkpoint orchestrates our CI/CD workflows, and its background job system represents the lifeblood of builds, tests, deployments, and releases at Slack. Checkpoint has an API endpoint that receives a webhook from GitHub when a new commit is created. From the single commit, Checkpoint enqueues different classes of background jobs that trigger Jenkins builds, which are like either builds or tests, DB updates for updating results in the DB, et cetera. The CI/CD orchestration service regulates the flow of requests through the system. One sec. And our teams aligned on implementing circuit breaker clients with multiple jobs calling the client. And the orchestrated consumer before sending requests to the next system. This means we can better manage different queues, and this leads to fewer retries in the remainder of the system. You might ask, well, what does a remainder look like? And this illustration is in higher res in the URL and shows an example flowchart of how Slack uses integration end-to-end tests to verify correctness for complex workflows that overlap multiple services. User commits and pushes their code to GitHub. GitHub sends a request to Checkpoint as a webhook, and Checkpoint enqueues the job itself to calculate and create Jenkins job requests. We typically see 1,000 PRs land over the course of a week, with 1,000 more concurrent PRs in flight. And each PR might have multiple commits that each require 20 to 60 test jobs, some of which might require builds. So while Slack started with a single service web app, today's Slack user experience involves multiple services that support testing workflows. Slack is a complex application with a number of configurations. For example, teams, enterprises composed of multiple teams, cross-enterprise messages. And so in this diagram, the web app test environment is comprised of multiple job, like a single web app API and multiple job queue workers. And to test more complex code paths, product and test engineers focus on writing expressive, automated tests which rely on a lot of moving parts, like complex team setups. So recall earlier we mentioned circuit breakers come in at the Checkpoint job queue level. It might detect a downstream system is not available. So in that case, let's make circuit breakers to defer work against systems when they aren't available or showing high error rates, and shed work for commits that aren't relevant anymore. And so typically, developers only care about test results on their latest commit. We chose this focus on circuit breaking with deferral and load shedding in Checkpoint background jobs relating to CI. CI represents the largest user, which is about 90% most days by volume, of background jobs in Checkpoint. While circuit breakers can live in client logic, for example, waiting for recovery or blocking to hold work, Checkpoint's background system presented better opportunity because it's the intermediary between multiple jobs and contains its own background job scheduler. And so leveraging the scheduler for job loading, Checkpoint can mark a job as complete without executing it. Leveraging the scheduling for deferral, background jobs can return open and then retry after a period when the circuit breaker is closed again and allow other background jobs to execute without blocking any individual executor. So here we see a background job called run test job that contains multiple circuit breakers. The scheduler calls the can-run function to learn about validity. And I'll talk through classes of these circuit breakers from this code block in the next slide. And so, let's talk about two different classes of implementation. In the first period, we focus on circuit breakers with metrics already accessible to Checkpoint, state tracking related to its jobs. So we load shed test executions for older commits on a branch. Again, engineers regularly push commits to their branch, and so older commits, we don't really care about those test results. And we load shed test retries for a suite that has consistent failures. We defer test jobs when Checkpoint and Jenkins queues reach a certain threshold. This builds up queues in Checkpoint scheduler. We defer test jobs on end-to-end tests when Slack test environments are already executing them. So some of these test jobs are dependent on services across the pre-production environment. So for example, Flannel, we mentioned this earlier, the edge cache in multiple regions worldwide that returns frequently fetched team-wide data. The tests. It's a source of truth for all customer data with MySQL syntax. Vitesse is a database solution for deploying and scaling and managing large clusters of database instances. And finally, search. A search service serving very large indices of messages, files, and people that computes a live collection fed real-time through the job queue and computed weekly with offline information from the beginning of time. And some of you might ask, well, how do we do this? We call Prometheus to programmatically understand metrics, using Trickster to fetch from different Prometheus clusters, keep these load balanced, and cached. We convert human-looking responses to pages from your favorite Grafana graphs to machines not running jobs until we see recovery. Over here, I show a little PromQL that you all know and love. And so we basically borrow PromQL queries from Grafana dashboards and programmatically call these to alert engineers that, hey, circuit breakers are opening, and when we see recovery, closing. And this is an example from a week ago. This circuit breaker for Flannel was open for about 3 minutes when we saw a small blip. This is a message from Checkpoint that sends an alert to alert CI issue, a channel that, of course, contains alerts when we see an issue in CI, that a circuit breaker is open. So the user experience, if you're doing development, you don't need to hit retry. The test results page in the Checkpoint front-end UI shows an open circuit breakers, and upon test completion, a user gets a DM. Things just kind of happen. Another benefit of these circuit breaker messages are links to multiple views of the same problem. So from that initial message, we have triage links to the runbook, various Grafana queries containing details to help us better ask questions. In this thread below, you see I post to the search team's triage channel that something bad is happening with the details. The search team then investigates, and then a bit later, the issue is fixed. And subsequently, the circuit breaker recovers. And so let's revisit that load graph and test execution graph from earlier. Before the circuit breaker implementation, we saw growth at about 10% month over month. And after this was implemented, over the last couple of years, I only show of course. I only show 1 year from March 2020 to March 2021. We saw growth of about 1.5%, so a lot more level. We made other changes in March 2021 to even more drastically cut load, but beyond the scope of this talk. Again, these represent a change in executing requests that we know will not fail, for example, on downstream systems that are down, or for changes that aren't relevant to the user. For example, an old commit on your branch. And so let's talk about what we heard about. We limited our blast radius. Over the last 2 years, we didn't have any cascading failures in CI. We still had issues, still had incidents, but no cascading failures. System resiliency increased for all CI/CD workflows over individual requests. Throughput increased and significantly reduced internal load for CI. We had faster and smoother feedback loops despite friction and load shedding. Developer metrics were at the time and still are aligned with fast feedback loops. These weren't affected negatively. And finally, we found a lot of leverage. We used the orchestration layer circuit breakers as a prototype to regularly look and develop intuitions for how the complex systems we have around the CI/CD ecosystem and customer use cases are affected. And so, how do we do this? Circuit breakers and checkpoint do not execute requests. We either defer or shed load against systems where we know the requests are against a system showing a high error rate or not available. The user feedback we provided users feedback for infrastructure tooling changes. Tools that abstract away changes might be confusing if it isn't clear what's changing. And so we do our best to communicate essential complexity and provide entry points to understand what bad things are happening in your system. And circuit breakers helped queue management isolation between services. No cascading incidents came as the result of this work. And we saw distributed systems, one thing we we remind ourselves, distributed systems evolve at different rates across services. And so we built for that. We discovered circuit breakers surface issues that our users encountered, and we had the potential to mitigate failure modes associated with that scale and complexity with no required user input. And so we created automation for federated, resilient metric lookups to tackle complex dependencies. The ability to programmatically look up metrics is a reusable tool in both circuit breakers and adjacent complex systems, for example, continuous deployment. And so with that, thank you all very much, and I'd love to open it up for questions.
Thank you so much, Frank.
Yeah, thank you.
So please, guys, help me with your questions at Slido. And let's wait. It will happen. So how do you feel now after the conference?
Yeah, pretty good.
First time in Hungary now.
Yeah, first time in Hungary. It's I'm really enjoying myself here.
It's amazing. So,
Should I go?
Come on, guys, help me out just a little bit. I don't want to be so ridiculous here for 1 minute. Just kidding.
Any questions? OK, cool. Thank you all very much.
Wait.
I'm not sure how this works.
We have something for you before you go. Oh, man. Thank you for participating. This is for Craft.
Oh, word. Thank you, Ramon. Appreciate that.
You're welcome, team. Thank you, guys.
A little early in the day, but I appreciate that.
Before you go, we have something else. Is where else has Slack adopted the circuit breakers?
Yeah. So let me. Can you tell us? Oh, no, you can't see this anymore. Oh. Oh.
It's here.
Oh. Could we? I had some extra slides just for fun. Can I switch back by any chance? Oh, yeah, there we go. Cool. So this is a kind of new project. We're currently using a very similar mechanism to think about automated deploys and rollbacks. So how might we go from continuous delivery, which is a human clicking buttons, to having machines automatically deploy code to canaries, baking, running tests against them, running redline, load tests, performance tests, and automatically deploy code without human intervention. And I had another slide that I seem to have accidentally deleted about how we use the same circuit breaker tooling to look at test suite metrics. But I'm not connected to Wi-Fi. Or else we could do a slightly more live demo. But we also use it to surface anomalies to test platform teams and to teams themselves that we're noticing a high rate of flakiness or failure rate, probably due to code change. And one of my colleagues and I co-wrote an article about how we addressed, and I alluded to this earlier, in about March 2021, we drastically changed the workflow on how we execute most of our test stack and worked with a lot of teams to realign and execute a whole lot less end-to-end tests to better create a pyramid and focus on medium-sized tests. It's in the blog article, sorry. I accidentally deleted that a few days ago, or maybe even this morning, who knows. So, yeah.
Great. Thank you. Okay, we have another one. What is the biggest disadvantage to use? I asked this already?
Main practice is reduce CI test load. It's really interesting. I think it really depends culturally how you all work. For our infrastructure, we work through a few different ways to think about this problem. One, I had mentioned this earlier, was working with teams to better parallelize. We are working through, around the same time frame, we work through how to better track dependencies. So we target what tests, whether they're unit or integration or end-to-end tests, how we perform that sort of calculation. And then use that as a scaffold for downstream tests to use to only run tests that are relevant to code changes. Also more recently, also don't have the slide. One of my colleagues is figuring out and is currently drafting an article on how we do test impact analysis. There's an article by Martin Fowler on, hey, how do you look at and start measuring and quantitatively getting a measure for what your hourglass, your test pyramid, your inverted pyramid starts to look like. And that has been a really good measurement for us to understand what parts of the code base are well tested, not well tested, and where we might have a lot of confidence releasing code to customers.
Cool. So please make an applause for our really nice speaker. And guys, let's have some lunch. Thank you.
Thank you.
Thank you so much.
Hey, thank you.
Thank you so much.